Hello, everyone. Welcome to today's webinar. The webinar today is on rare earth magnets, yesterday, today, and tomorrow, and presented by Dr. John Ormerod. I'd like to, as a moderator, I'm Cynthia Howell. I am the moderator today, and I'd like to, again, walk you through a few things before we actually get started with our webinar presentation. I'm with the Education, Training, and Outreach at CMI. And today, again, for our webinar, we have a few webinar etiquette pieces that I'd like to share with you so that things will go very smoothly. First of all, our webinars are broadcasted by Colorado School of Mines. We're broadcasting live here right now. And we are always looking for great topics in the future. So if you happen to have a topic, please make sure that you add that to the exit survey that we have at the end, and or contact one of us. This is a public webinar, and a recording of this is going to be at cmi.aimslab.gov in about a week. And also our presenter today would like to take questions at the end of the presentation. So I will help him with moderating those questions. However, when you have a question and it comes to mind, please don't hesitate to begin typing it. We are using the question answer box methodology today. So type it in and it will be queued in order so that when the presentation ends, he'll be ready with questions and faced with questions immediately. That is ideal. I'd like to introduce our presenter today, Dr. John Ormerod. He has a BS, MS, and PhD in metallurgy from the University of Manchester. He also began his magnetic career with Philips in the UK and Holland. He also is on many advisory board members for Bunting Magnetics. He's a senior technology advisor for MAI and technology advisor for Niron Magnetics. And he's founded his own business. And today you're going to hear a little bit about his vast area of expertise in the magnet area. And what I'd like to do is, again, not take any of John's time. I'd just like for him to take it over from here and present to you his rare earth magnets yesterday, today, and tomorrow. Okay, John, if you'll take it away.
Okay, thank you, Cynthia, for that introduction. Hopefully you can see the presentation. Okay. Well, first of all, good afternoon, everybody. Thank you for joining us today. I appreciate that. As you just heard, my name is John Ormerod, and today I'm representing Magnet Applications Incorporated as their Senior Technology Advisor. The title of this talk is Rare Earth Magnets Yesterday, Today, and Tomorrow. So what I'm hoping to do in the next 40 minutes or so is give you a flavor of the development of the rare earth permanent magnet industry and the markets it serves, talk about current technologies and materials, and highlight some interesting developments. Now, given the time constraints, and this is a rather broad subject area, I'm only able to cover the topics in a very rather cursory manner. However, I'm happy to answer questions, provide more detail for anybody who's interested. You can contact me anytime via email or even by phone, and I'll give that contact information will be available at the end of this presentation. So I always like to get the ball rolling on these talks with some sometimes humorous quotes, and I've actually got a couple of quotes today that relate to research, because I'm assuming that most of the audience for this webinar is involved in research of one type or the other. So here's the first one. And it's attributed to Albert Einstein. And I don't know whether he actually said this, but here it goes. If we knew what we were doing, it wouldn't be called research. And there's another one that's very similar by Werner von Braun. Basic research is what I am doing when I don't know what I am doing. So I thought the audience might enjoy those too. So here are the areas I want to cover today. I want to start with an overview of markets and applications for rare earth permanent magnets. and then move on and talk a little bit about the history of the development of the of rare earth magnets, review current materials and technologies, say a few words about future trends, and then finish with some final thoughts. So let's start with markets and applications. Now here's a chart that I'm guessing many of you have seen before in some form or other. What it shows is the historical development of permanent magnets based on their maximum energy product, which is the universal metric of permanent magnet performance. And obviously, this is primarily through the 20th century. What you can see in this chart is the dramatic improvement in magnetic performance of these materials, beginning with the magnet steels in the early part of the 20th century. And in this case, the coercivity in these materials was determined by some strain-induced mechanism. We then got an improvement in coercivity and ultimately energy product when we moved to the Alnico type materials. And the coercivity in these alloys was developed through shape anisotropy. And eventually we moved to the hard ferrites and ultimately the rare earth permanent magnets, where high coercivities and ultimately energy products was achieved through a strong magnetocrystalline anisotropy. Now, one thing I will point out, in my opinion at least, there has been no major new material introduced in the permanent magnet industry since the introduction of magnets based on, or materials based on the Nd2Fe14 boron phase. And that was back in the early 1980s. So obviously it's well over 30 years since there's been a brand new material introduced into the permanent magnet world. So it does really beg the question, is it time for a new breakthrough in this area? Now, it's true to say that any magnet material that has ever been commercialized is probably still in some use today in some form or other. Even platinum cobalt magnets are still used in defense and aerospace applications in a limited form, obviously. But in my opinion, there's really only 5 classes of permanent magnet material or types that are commercially important. Starting with, we have hard ferrites based on the M-type exoferrite compounds, cast and sintered alnicos, isotropic bonded neodymium ion boron magnets, sintered samarium cobalt, and sintered neodymium ion boron. Now, this simple chart I'm just showing here illustrates a point that's been raised by several people, and that is there's really a gap in the properties of the available materials, from the high end of bonded neodymium ion boron at, let's say, 12 megahours Ørsted to the low end of sintered samarium cobalt at between 18 and 20. And this has been identified as an opportunity for the so-called gap magnet. Now, I have a slightly different perspective on this opportunity in terms of a gap magnet, and I'm going to share that with you later in this talk. Let's move on and talk about the market for permanent magnets in general. And I'll be honest here, it's very, very difficult to get good estimates of the size of this market. And indeed, there's not good agreement by the so-called experts who work in this field. But here's my estimate of the global permanent magnet market, at least in 2016. And it's approximately, in total, about $17 billion. Now, what I want to point out is, permanent magnets are clearly are critical for the functioning of modern society. But the market is relatively small at 17 billion. And just to get this into perspective, I just looked up what the size of the pizza market in the US is. 44 billion, just to calibrate you here. Now, what I'm showing now are those estimates of the permanent magnet market, shown as share in terms of the material classes. And what this simple pie chart illustrates is that the market for permanent magnets is dominated by two material classes: sintered neodymium-ion boron and hard ferrite magnets. And as you can see, they account for well over 90% of the all permanent magnets that are produced and used in the world. A few words about the function and applications of permanent magnets. Now, as far as I know, the only role of a permanent magnet, when I think about it, is to provide a magnetic field in either a substance or a vacuum. Now, how that field then goes and interacts with a conductor, another field, a charged particle, or another magnetic material is how a magnet provides a useful function in an application. So here's a table of the four major application categories: the governing physical laws, and the magnetic parameter that really determines the functionality of the magnet in the application. So at the top here we have electrical to mechanical, and then these are typical examples would be permanent magnet motors, hard disk drive, optical disk drive, voice coil motors, loudspeakers. Then we have mechanical to electrical. So these are generators, microphones, alternators, and so on. Magnetostatic field energy to mechanical work. So these are holding type devices, magnetic chucks, conveyors, magnetic separators, and so on. And then finally, electrical to mechanical, where the action is on a free charge particle. So these are traveling wave tubes, magnetrons, MRI systems, and so on. Now, when you look at the market segmentation by application type, what's kind of interesting is these three: motors, hard disk drive, optical disk drive, voice coil motors, and spindle motors, and generators actually account for over 60% of all the applications that permanent magnets are found in. So these are all rotating machines, and I just found it interesting that they really dominate the market in terms of usage of permanent magnets. Now, in terms of a market segment or an industry segment, I think probably everybody knows the automotive sector is by far the largest user of permanent magnets. And the type of magnet that was dominant in these applications a few years ago were hard ferrite magnets, and they still are to a large extent. But this is an interesting slide in that it shows, and this is from TDK, it shows in blue applications in the automotive market that are now, the neodymium-ion boron magnets are being used. And you can see some of them are 100% neodymium-ion boron, others are maybe 50%. And even more interesting, some of them are under the hood applications. So this is a trend that I started within the last 10 years, maybe within the last 5 years, and appears to be accelerating. So a very interesting trend. A couple of slides now showing major application areas for rare earth magnets, and I'll call them guesses of the magnitude of the rare earth magnet consumption in those specific applications. And the first one is hybrid and electric vehicles, and we're all aware of the dramatic penetration of this type of transportation in the automotive world. And in fact, it's forecast to become the largest consumer of rare earth magnets in 2025. Forecast this year for electric and hybrid vehicles globally is 25 million units. And by 2020, 18,000 tons of rare earth magnets will be used in those applications. Electric bicycles is, believe it or not, another very large and growing application area. Estimated 13,000 tons to be used in those devices in 2020. And then I mentioned hard disk drives, and particularly for voice coil motors, but also spindle motors in hard disk drives. It's interesting because this application, in my view, really helped to develop the early neodymium-ion boron industry. Now, today, of course, solid state memory and cloud storage is cannibalizing the application of neodymium-ion boron in desktop and laptop PC hard disk drive applications. But this year, it's still anticipated it'll consume 8,000 tons of rare earth magnets. Direct drive wind turbines. Again, a large and growing segment application area for rare earth magnets. 2020 expected to consume 25,000 tons. I've already mentioned automotive, and here we're talking about the conventional internal combustion engine. There's well over 100 permanent magnet devices in a typical car today. And on the rare earth side, we're estimating will consume 12,000 tons in 2020. General industrial commercial motors, very big area for permanent magnets in general, but rare earths in specifically. And as I mentioned earlier, rotating machines is the single largest application category. Acoustic transducers, now it's not necessarily a large tonnage of rare earth, but there's many million magnets used in this application. If you think of your smartphones and mobile devices, all have numerous very small transducers that are using rare earth magnets. And then finally, a technology that I think could become a major application area for permanent magnets is magnetocalorific cooling for both refrigeration and HVAC systems. Okay, let's move on and talk about the history and development of rare earth permanent magnets. It's actually interesting to note that by a combination of directional solidification and thermal magnetic processing, alnico magnets back in the late 50s, early 60s were developed with energy products up to 13 megaounce Oersteds. However, it became apparent that both industrial and academic researchers realized that any future major advances in energy product would require increases in coercivity past what could be achieved by shape anisotropy. And so this led to the search and shifting emphasis to crystal anisotropy. So in the 60s, the search began to identify uniaxial compounds that combined high saturation magnetization with high magnetocrystalline anisotropy. Now, the rare earths intermetallics were of particular interest because it was well known that the rare earth elements displayed magnetic ordering and large moments at low temperatures. The rare earth elements also tended to form intermetallics with the 3D transition metals. And there was a strong coupling of the rare earth moment with the transition metal lattice. So just to remind you, I mean, in order for a compound to be a potential candidate for a permanent magnet material, it really needs a combination of these basic attributes. It has to have high saturation magnetization. It has to have Curie temperatures significantly in excess of room temperature. And then it has to have a large magnetocrystalline anisotropy. And importantly, that has to be coupled with a magnetically unique crystallographic axis. Now, when these considerations were taken into account, it was really narrowed the candidate compounds to rare earth cobalt-5 and rare earth 2 cobalt-17. And this ultimately led to the development of the samarium cobalt-based magnets on either the binary samarium cobalt-5 or the multi-component samarium 2 cobalt-17 precipitation hardened type materials. Now, what happened next was there was a search for a combination of a light rare earth element with iron. Now, unfortunately, unlike rare earth cobalt, the rare earth iron system tend to form much fewer intermetallics. And those that do form tend to have low Curie temperatures and also display planar anisotropy. So it was realized that the binary systems were probably not going to provide a suitable candidate material. So the search was open to multi-component systems and metastable phases. And what happened was there was a simultaneous development and announcement of magnets based on the ND2Fe14b tetragonal compound. And these were discovered by General Motors Corporation and Sumitomo Special Metals Corporation. Now, a little bit of, just let me give you a little bit of a side here. Sumitomo Special Metals eventually formed a joint venture with Hitachi, and that eventually merged as Hitachi Metals in the late 2000s. General Motors spun off their neodymium iron boron magnet business as MagnaQuench, and today that's part of Neon Materials. Both set of researchers discovered the same compounds, but the processing routes were very different. Hitachi's process is based on powder metallurgical processing, whereas MagnaQuench is based on melt spinning or jet casting, and I'll talk about those a little bit more in this next section. So, current materials and processes. And I'm going to start with the powder metallurgical approach. Now, here's a very generic process that really applies in principle to both samarium cobalt and neodymium iron fully dense magnets. So we start with the raw materials. We melt, typically under vacuum or inert gas. That alloy is then cast into some sort of process. That solidified material is then crushed to a coarse particle size. Those coarse particles are then milled to around 5 microns typically to form single crystals that can then be placed in a die cavity. A magnetic field's applied, the single crystal particles orient, and they're compacted in a press to form a green compact. That compact is then sintered to full density, typically heat treated to develop the final magnetics, and then they go through a series of machining operations to provide the required mechanical tolerances and shapes. And the magnets can either be magnetized at the magnet production facility or at the application, as they're either being built into the application or actually in the application. Now, what I want to show here is actually a much more detailed process that is typical for a neodymium iron boron magnet. And in this case, with neodymium iron boron, we start with the melting and casting is through a strip casting process, where the cooling rates are much higher than is typical for, let's say, an ingot casting. Here we're talking about cooling rates in 10 to the 4 degrees per second rate. That alloy is then crushed to a coarse particle size through a process called hydrogen decrepitation, milled in a jet mill, pressed and aligned, sintered, heat treated, finished ground. And then in the case of neodymium iron boron, because of their poor corrosion resistance, those magnets are almost always coated in either a metallic or a polymeric coating to provide the necessary corrosion resistance. Now, I just want to talk about three of these process steps, which are actually upstream processes that I personally believe have really contributed to the improvement in the magnetic performance we see in these materials, and to a certain extent their corrosion resistance. And it's strip casting, hydrogen decrepitation, and the fine powder milling process. Let me just go through those in a little bit more detail. Now, starting with strip casting. I mean, in sintered neodymium iron boron magnets, the microstructure of the starting alloy is critically important to the generation of the final magnetic properties of the sintered magnet. Now, the major problem with producing neodymium iron boron alloy is that the Nd2 Fe14B intermetallic forms from the melt by a peritectic reaction. Now, at normal cooling rates, i.e. ingot casting, that reaction does not go to completion. You end up with large grains of 214-1, and then a boron-rich phase, some neodymium-rich phase, and a lot of alpha iron precipitates out. And the alpha iron is a real problem when it comes to crushing and milling the powder. And of course, if it gets through to the the final sintered magnet, it really spoils the magnetic properties. So what was discovered by quenching from the melt at a much faster rate, at as I said earlier, 10 to the 4 degrees per second, you could suppress that formation of alpha ion and produce a very uniaxed structure of the 214-1 surrounded by a very fine-grained neodymium-rich phase, which is essential for the development of good sintered magnetic properties. Hydrogen decrepitation. And what we do here is we take the strip cast material, put it in a vessel, and apply hydrogen pressure. The hydrogen is readily absorbed by the neodymium-rich phase at the grain boundaries. The lattice expands, and literally the material falls apart and produces a very friable, brittle, coarse powder that is very readily milled and produces high milling efficiencies in the subsequent process, which is jet milling. What this process does is it produces a very narrow particle size distribution around the target average particle size, which is required, and at the same time removes harmful ultrafine high rare earth content particles. So in my view, all these three upstream processes have really contributed to the excellent magnetic performance we see in sintered neodymium ion boron based magnets, and indeed the market acceptance of those materials. Okay, let's move on and talk a little bit about the General Motors or the magnet quench process. And here they pioneered the use of melt spinning. Now, melt spinning consists of melting the alloy or the elements in some sort of tube. That melt is then sprayed onto a rapidly rotating disc or wheel, typically water cooled, and cooling rates in excess of 10 to the 6 degrees per second are achieved. Now, General Motors or Magnet Quench commercialized this technology, and it's primarily used today for producing isotropic powders that are mainly used in bonded magnets. I want to move on a little bit now and talk about one of the major disadvantages of materials based on the 214-1 compound, and namely that's their performance at elevated temperatures. So here's an example of the demagnetization behavior of a sintered neodymium ion boron grade N55M. And what you can see is the effect of increasing temperature in that it reduces both remanence and coercivity. And in fact, if you look at coercivity, we lose about 50% of the room temperature coercivity at 100 degrees C. Now, this is potentially a major issue in any application that's operating at elevated temperatures. For example, a servo motor that has to run at 100 or even higher temperatures. If these magnets are subject to high demagnetizing fields at startup or where high torque is required, depending on the design, it's highly likely that the magnets will be permanently demagnetized, and of course lead to the loss of motor performance. Now, it was known from the very early days of neodymium ion boron development that the substitution of certain heavy rare earth elements improved coercivity. And this chart on the left here is actually from a publication way back in 1984 by the Sumitomo Special Metal team. And what you can see is that the substitution of dysprosium into the ternary system dramatically increases the coercivity. Now, unfortunately, there's some loss in remanence because the heavy rare earths tend to couple antiferromagnetically with the iron lattice and reduce magnetization. But coercivities are dramatically improved. So it's become standard and common practice to add dysprosium or in some cases terbium to improve the coercivity and thermal performance of these magnets. And if you see the chart on the graph on the right shows excuse me, the impact of various levels of dysprosium on the maximum application temperature. At one extreme, if we have very low levels of dysprosium or even zero dysprosium, those magnets can't really operate above 80 to 100 degrees C. Whereas at between 10 and 12 weight percent dysprosium, we have magnets that can operate in applications above 200 degrees C. So that really became the solution to the poor thermal behavior of the ternary system. Oops. Okay, then 2011 and 2012 happened, and rare earth prices essentially went crazy. And what we saw obviously was this big spike in price, and particularly dysprosium oxide price increased 50-fold in literally a few weeks. So what happened, there was a major investment made around the world in the search for either rare earth free substitution or efforts to reduce dysprosium content for the higher temperature, higher coercivity grades. And what one of the things that happened was that several major magnet producers developed essentially the same approach, or at least similar approaches, by using processes that enrich the grain boundaries of the main Nd2Fe14b phase with dysprosium. And they used a variety of solid state, gaseous, and other forms of diffusion technologies. Now, it makes sense because the coercivity mechanism in the 214-1 based materials is determined by the grain boundary regions. So in a sense, the dysprosium within the grains isn't really contributing to the coercivity. So these dysprosium diffusion processes, did several things. Obviously, they reduced the amount of dysprosium in the magnet. They enhanced coercivity, but at the same time, they reduced the loss in magnetization because it was only concentrated at the grain boundaries. Now, I do want to mention that fully dense, oriented neodymium iron boron magnets could also be produced from melt spun powders by a variety of hot pressing and hot forming technologies. And here's an example of actually a joint venture that was formed between Dido Steel, a magnet producer, and Honda. And what they're doing, they're producing from melt spun powders. They cold press, hot extrude, and produce radially oriented ring magnets that are used in hybrid electric vehicle traction motors in Honda vehicles. And the other interesting thing to note is there is no, at least they claim, there is no heavy rare earth element content in these magnets, even though the traction motors obviously have to operate at elevated temperatures, certainly in excess of 150 degrees C. Now, I think the main reason is because these magnets are starting with melt spun alloys, and so they're beginning with a much finer grain size, at least a factor of 10 less than the sintered magnets, which enhances the coercivity. And in fact, if you look at this chart, it's a little bit hard to see, but what it's telling us, if you have a motor that can tolerate, and this is at 180 degrees C, tolerate a coercivity of maybe 6 or even 7 kiloersteds without demagnetizing, you can use these hot press magnets with 0% dysprosium or terbium. Now, if you need higher coercivities, there is some dysprosium required, but what they're claiming here is it's probably around 4%, 4 weight percent less than in the conventional sintered magnet. A quick word about samarium iron nitride. Now, the samarium-2 iron 17 N3 compound was actually discovered shortly after the discovery of the Nd2Fe14b phase back in the 1980s. However, for a variety of reasons, the commercialization of this material has been limited. Again, the process starts with melt spun materials. It's annealed. The powders are then annealed and then nitrided at a relatively low temperature. The powders are then used in bonded magnets. Now, several companies claim to produce these powders and magnets on a commercial scale, but the big issue is the 217(3) compound is metastable and actually decomposes above about 550 degrees C. So fully dense magnets certainly aren't possible by sintering, and even hot pressing, hot forming cannot produce fully dense magnets of this compound. And finally, let's have a word about a magnet material that, as I mentioned earlier, hard ferrite, is produced in the largest tonnage in the world. This is now benefiting from the doping of rare earth elements. And what's been found is both saturation magnetization and magnetocrystalline anisotropy can be improved by the addition of lanthanum, and also cobalt helps. And these magnets are now available with a 40% improvement in energy product over the conventional strontium hexaferrite magnets. Okay, let's move on to a couple of developments that I've received some interest recently. The first one is an announcement by Toyota. Toyota created a bit of a stir earlier this year when they announced a low neodymium high temperature magnet. Now, there's not a lot of information available, but from what I can glean, it appears to be again, they're starting with a melt spun process, but it's a lanthanum cerium substituted NdFeB alloy, where it appears they then diffuse neodymium at the grain boundaries to enhance the coercivity and magnetization over the lanthanum cerium alloy. And my speculation is they're using hot pressing and hot forming to densify the powders. But once again, there's a limited amount of information available at this time. The second area I want to talk about is 3D printing or additive manufacturing of magnets. Now, I'm sure most of you are aware, Oak Ridge National Labs is one of the largest additive manufacturing material extrusion installations, certainly in the US and probably in the world. And it's referred to as the Big Area Additive Manufacturing or BAM process. Now, we at Magnet Applications provided the feedstock material to run through this process. What we did, we took Magnequench type isotropic powders and we compounded them with a thermoplastic nylon 12 resin through a twin screw extruder. And as I say, that provided the feedstock for the BAM process to produce some magnet bodies. Here are some of the magnetics that were achieved, and I'll just point out this top left-hand demagnetization curves. What's interesting and was surprising to us, the orange demagnetization curve is from the BAM, the extrusion process. The blue is from a conventional injection molding using the same compound. So obviously we were surprised to see that the BAM process actually had better properties in terms of remnants and coercivity and energy product than the injection molding process using, again, the same compound. We think what's happening is there's a much shorter residence time of the compound in the BAM process compared to injection molding. And what's happening is this is limiting the particle mechanical damage and oxidation and results in improved properties. Now, one interesting advantage of this extrusion or BAM process is, as the name suggests, you can produce some very large bodies and you can produce some very large magnets. This is an example of a ring magnet, 6 inches long, 4 inches outside diameter, produced in the BAM system. Trust me, this would be very difficult to produce by conventional injection molding. Okay, I'm probably getting a little bit towards the end of time here, so let me just a few final thoughts. Now, as I mentioned earlier, to me, it's really intriguing that two material types dominate the market for permanent magnets: hard ferrites and sintered neodymium iron boron. Now, what's really interesting is these materials are really at the opposite end of the performance spectrum in terms of magnetic performance. They're also at the opposite ends of the cost or price spectrum. So this got me wondering is why are some materials so dominant in a market, and in this case, the permanent magnet market, and others are basically become niche materials? So I wondered, is there an optimum price performance metric that helps to explain this dominance of certain materials in a certain market? So what I did, I took the data from the market data I showed earlier, or at least my market estimates, and I calculated an average dollars per kilo, and this you see in the second column on this chart. I then took a stab at estimating what's the average energy product within these material classes, because of course there's a range of magnet grades within a material class. And then I just simply divided the average price by the average energy product. And lo and behold, it turned out that at least to one decimal place, the materials that dominate the market have the same price performance ratios. All the other materials have much higher, well, I won't say much, have higher price performance ratios. Now, the way I think about this is the lower that number is, the more efficient the material is in converting the dollars you pay to the energy output, the magnetic energy output. So the lower, the more efficient it is in converting dollars to energy output. And of course, the higher the number, the less efficient that conversion is. So what I did, I've just plotted out on this matrix the energy product and the dollars per kilo for these 5 different material classes. And I also put on there the dollars per kilo per megawatt Ørsted, this metric, price performance metric line at what appears to be the optimum number at 1.9. And what I'm speculating here is that any material in that yellow area is going to have a lower price performance ratio, i.e. it's going to be more efficient. And this is going to be where the mass market materials will be. Anything in the pink area, the price performance ratio is going to be higher, and therefore it's going to be less efficient. And there will be some materials, and we have those materials today, that find some niche market applications. Now, this gets me back to what I mentioned very early on in this talk about the gap magnet, because here's what I think the gap magnet opportunity is. It really lies between the high end of hard ferrite and arguably the low end of sintered neodymium iron boron in terms of energy product. So we're talking about, you know, anything between 4, 5, maybe up to 40 megawatt Ørsted. So it's a very wide opportunity in terms of magnetic performance. However, obviously the trick is you've got to get the cost per kilogram to give you a ratio that is less than 1.9. And that's really the trick to get a new material that becomes a mass market material and can compete with the existing sintered neodymium iron boron and hard ferrite magnets. So with that, I will I thank everybody who's listened to this, and I appreciate your attention. And obviously, any questions I'll attempt to answer, or you can contact me at these I think I've got these email addresses, or by phone, whichever you prefer. So thank you.
John, thank you so much for a great presentation. We would like to open up the floor for questions. And if you take a look at your question and answer section, first, We did have a question from Brian Andrews, and this was actually even before the webinar started. Do you see that one in the answer queue?
Yes, I do. I do.
Okay.
Okay. So did you know that, did you know the Mountain Pass, California mine is supposed to open back in about a year or so? How will this impact our rare earth element supply in regards to neodymium and dysprosium for magnets? Brian, what I know is some sort of consortium have purchased the assets of the mine, and there's lots of rumors about what's going on. But so I'm a little bit reluctant to comment with any specificity. The only thing I would say is my understanding is the main mineral or the ore at that mine is bastnasite, and those ore bodies are not very rich in heavy rare earths, is what I recollect. So I doubt if it's going to do anything for dysprosium, if it does anything at all. That's probably all I can say on that at the moment. Okay, then we have an anonymous attendee. Is there a lot of material lost in the melt spinning process? If so, how much? I don't know. I don't know. That's not an area I've worked in terms of manufacturing. I'm guessing, you know, this process has been around over 30 years now, so I'm assuming that that the Mainiquench guys have kind of got this under control, and they're achieving, you know, pretty good yields. But I can't speak with any first-hand knowledge on that one. Ryan Sales, do you think that the Toyota lanthanum cerium metal have cobalt added as well? I don't know, Brian, because again, there's no information. There's not a lot of detailed information that I've been able to find. I mean, possibly to improve, to get improvements in Curie temperature, but I honestly don't know. What do you estimate the market for the gap magnet to be? I'm sorry, who's this from? Eric Schweigler. No, sorry, that's the wrong one. His questions seem to be clicking in, and just a second. Brian, it's Brian Sales again. Does the 1.9 number account for losses during manufacturing? Well, yeah, I mean, it does, because it's really based on the sales price, Brian. So it's not based on, I haven't based it on cost, because the sales prices are hard enough to get, but the costs are almost impossible to get. So that ratio is based on the sales price. Now, I do want to say one thing, that I'm cheating a little bit. Well, I'm cheating a little bit. I'm cheating a lot. To use dollars per kilo is not, or dollars per unit weight is not the right way to look at this. I really, and I'm going to do this when I get the 2018 market data together, which I'm working on at the moment. I'm going to redo this analysis and look at it on the basis of dollars per unit volume. Because the thing to remember is we don't buy magnets. We don't buy magnets on a weight basis, and we don't use them on a weight basis. We buy them and use them on a volume basis. If if somebody's specifying a magnet, they provide the magnet supplier a print that has dimensions. There's no mention of weight. Now, so where that becomes why that's important is because all these different materials have different densities. We're going from hard ferrites at 5.0 grams per cubic centimeter up to samarium cobalt at 8.5. So this really should be looked at on a volume basis. And as I say, I'm gonna do that when I get the 2018 numbers together.
And John, would you go back to the answered section? I was a little bit too hasty, and there's a question there from Melinda Thatch at the bottom that actually did not get answered.
Oh, I'm sorry. Where did you estimate the
That was my error.
That's the one I was starting to read. Okay, okay. Hey, Melinda, where do you estimate what do you estimate the market for the gap magnet to be? I don't know whether I can estimate it, because it depends. If you could, in theory, if you could get a ratio, and again, I'm doing it on a weight basis, and I accept it should be a volume basis, but let's just, you know, keep the weight for the moment. If you could get a ratio that is much lower than the 1.9, in theory, this new material would start to cannibalize the hard ferrite and native iron boron applications of today. Plus, it would create new applications where, you know, we're probably using electromagnetic alternatives or even other technologies. The trick is to get that ratio to be less than 1.9 on the weight basis. Okay. Eric Schwegler, how do melt splitting cooling rates compare to laser AM processes? I don't know what the laser AM process cooling rates are, but you know, I know melt spinning is typically 10 to the 6 degrees per second, but I can't help you how that compares. And John, I think it's QE, but I probably got that wrong. I'm sorry, I apologize. What alternative non-rare earth element magnet materials you think may have a viable path forward? I know there's some work going on lower cobalt alnico magnets. Well, let me put it this way. There's a big distaste, I'll use that word, for any magnets that contain cobalt. So anything we can do to eliminate cobalt in any of these materials is going to be a benefit. And obviously the same thing is happening with the rare earth elements. There's several groups working on what would be the holy grail of permanent magnets, but as far as I've seen, there really hasn't been any announcements in terms of commercial materials. But that is magnets based on the Fe16N2 compound. It's certainly got very high magnetization. The trick is getting some coercivity out of it, out of that compound. But if there was ever a holy grail of permanent magnet materials, it would be magnets based on Fe16N2. Can you elaborate on applications for defense platinum? It's platinum cobalt, actually. This says iron platinum, assuming it's not classified. Or more broadly, any applications where specific requirements drive choice of a surprising material? I don't know specifically on these cobalt platinum applications, other than some of them are probably, you know, defense related, aerospace, satellite applications that were probably designed way back to use platinum cobalt, because that was the only, I mean, platinum cobalt is a very stable, thermally stable, and has reasonable coercivity. And I think there's just a reluctance to, you know, to redesign into anything else. But I can't really be more specific than that. Kajitan, is the bonded magnet price performance based on isotropic magnet? If yes, what changes do you anticipate with isotropic? The answer is yes, it's based on isotropic. This, you know, all my numbers are based on the biggest market for bonded neodymium iron boron, at least today, is in the isotropic variety. There's very, I mean, there are some people who produce anisotropic powders and magnets, but it's a lot less than the isotropic variety. I don't know. I need to get some data, and I'll add that I'll add that to the analysis. But at the moment, I think I would say the anisotropic bonded neodymium ion boron market is significantly less than 1% of the total. So I've chosen to not include it. Perens, do you think samarium nitride bonded magnets could play a role for gap magnets since sintered magnets are not possible? I don't think, well, it depends what you mean by gap magnet. I mean, if you're referring to my interpretation of the gap magnet being in the mass market region, no, I don't think they can. I don't think you can get the price performance ratio. Is there an opportunity of a gap magnet that could be some niche application? Yes, yeah, I think that's possible. But it would probably have to be an anisotropic variety that you're getting some, more significant energy product out of than an isotropic neodymium ion boron bonded magnet.
So we are getting to the top of the hour, but we do have time for one more question, if we might have one out there, if anybody is in the process. In the meantime, I'd like to thank you again for such a great presentation on rare earth magnets, giving us a thorough yesterday, today, and tomorrow. That has been, again, just very helpful for our CMI team and others who have joined that don't know much about magnets. I would like to thank everybody for attending this webinar. And again, remind you that if you have a suggestion for a future webinar topic or presenter, we would love to hear from you. And information on the next CMI webinar, because they are a series of webinars that we do monthly, they're going to be listed in the critical times at cmi.aimslab.gov. Looks like we might have one more question, is that correct? By Brian Andrews.
Brian, okay. Has there been any research into coating so that the heat doesn't affect the magnets? No, not that I'm aware of. I mean, all the, obviously the coating development and research work has all been focused on improving the corrosion performance, resistance of these magnets. Yeah, I mean, thermally, I mean, it's an intrinsic property issue. If the magnet sees 100 degrees centigrade, then the demagnetization curve is going to look like the one I showed earlier. Now, I guess if you can insulate or isolate the material from the thermal source, yeah, that might be a possibility. But I think the answer is to your question is really no.
Again, thank you for everybody attending. This has been, we appreciate all the questions. Don't hesitate to contact John in the future if you have additional questions based on this webinar. And a reminder that this will be at cmi.aimslab.gov website for your viewing in the near future in about a week. Thank you, everyone.